We're doing volumes of solids, right? Volumes of solids. So I want to remember the key idea behind net accumulation. The key idea behind, or one of them, a very key idea, it was what? The rate of change at the current value of x as x increases through the current delta x interval. The rate of change at the current value of x as x increases through the current delta x interval. So we've seen this before, so a couple times. In the first week, we said the approximate net accumulation function was, what is, where's my pen? We've got a lot to do, so everything needs to go smoothly. We're off to a bad start. There we go. Okay. Now will this work? There we go. Okay. So what was this about right here? So our approximate net accumulation. Remember what this was about? Everything until the current interval. And by everything, what does that mean? Everything. All the accumulation from, what do we call those delta x's, right? Completed intervals, right? So this is like history, right? Past. We've already made it through a bunch of completed intervals, and this would be all the accumulation from those completed intervals, right? And then this is about, what was this about? The accumulation so far in the current interval, right? So far in the current interval. And so what I want you to pay attention, and with volumes, this idea is really important. To get the accumulation in the current interval, we need the rate at the current value of x, right? At the current value of x is generating, by multiplying it by dx, it's giving us that amount of accumulation in the current interval. And this is a really, for volumes, this is a really key idea. Because we're going to see the same thing with these volumes of solids. We're going to have all the accumulation from past intervals, past elements that we've already created. And then we're going to look in the current interval and we're going to ask, what's the rate of change? How is that current element changing? What is the rate of change? And if it's a solid of revolution, we saw two cases, right? Either what the radius is changing, and that's creating the rate of change by an increasing radius, or what else? The height is changing, and so our rate of change is according to that. So we saw those two cases. Okay, and then we saw this with area as well. Remember this. We said we need to know the rate of change, right? We need to know the rate of change in order to accumulate signed area. And what was the rate of change that we wanted? We're looking in the current interval. We needed that constant rate of change for that whole interval. And what was that? If we were looking at area, signed area for the function f of x, what was the rate of change? What was the rate of change in the current interval? The value of the function, right? The height of the rectangle. So right now the rate of change is about 1.6 something. That's about 1.63. So and that was how we set up those integral functions to find net accumulation of signed area. We needed that rate of change. And that's always about what the rate of change at the current value of x. For area, it was the height of the function. That was our rate of change. That's how fast the signed area was changing. We saw was the height of the function. Okay, so volume is going to be similar. So I want to kind of recap the example we were doing last time. Okay, and so remember, so we had, do you remember this interval, this region that we had? Okay, and we said we wanted to rotate this around the y-axis. Okay, Rotate this around the y-axis and imagine the shell, the empty shell that would be formed. That's how we always want to approach these. Start with our region, get the boundaries of the region, rotate it as they tell us to rotate it, and then imagine or sketch the empty shell that region creates after the rotation. So here's a visual of that. Okay, so we're going to rotate that around. And we're going to get this shell. Let's unrotate a little bit. But where's the shell? So do you see the bowl part that's formed by the x squared? Is the shell that we're talking about above or below the bowl? Below, right? The empty shell is the part that's below. This one, that out, there you go. So as we rotate that thing around, our empty shell is this here. So we've got that identified, and it's going to go all the way around the y-axis, and we're going to get this shell, and now we want to fill it. And so the first thing we said, let's fill it according to delta x intervals, right? So we're gonna slice this thing up into delta x intervals, and imagine filling as x increases through delta x intervals and creates cylinders, right? Let me just put this over to the side here. So we'll keep that image in mind. And so now we're going to fill that thing over there to the right. We're going to fill that with cylinders according to delta x. Now this line right here is showing the current value of x, okay? That line right there is showing the current value of x, so I'm going to let x increase. And you're going to have previous intervals, so shells that are already completed, and then you're going to have the current interval, right? The current interval. As x increases. So in the current interval, how is each cylinder increasing? Is its radius increasing? Is its height increasing? Or are both increasing? Radius, the height, or both? In the current interval. Most of you are saying only radius. Is that what you think? Only the radius, okay? So yeah, so the current cylinder is the one that has the greenish top to it. Green, is it green or blue? Gray. Okay, we'll go with gray. All right, so it's the one with the grayish top, right? The grayish top is the current cylinder being formed. And are we in agreement that what dimension of that is changing as x increases? The radius. Is the height changing? No. Okay. So that's gonna that very fact frames how we're gonna get the rate of change of our volume as it's increasing. It's that the radius of these things are increasing and the height is not. Now, from one cylinder to the next, the height is different, right? But what do we care about? We care about, like I said earlier, we care about the rate of change at the current value of x, right? So you don't want to look globally. You want to look locally at the current value of x. What's changing? What's changing? The radius. And so we know then, we've explored or investigated this kind of cylinder before. When the radius is changing, like that, pause it. What is the rate of change of volume of that cylinder? So that one with the grayish top, what is the rate of change? So we say rate of change of volume at the current value of x is, he wants 2 pi RH. Remember that? It's the same value as the area of the vertical lateral surface. Right? That's, and you guys worked that out last Friday, was it? So 2 pi RH. Okay, but we need everything in terms of x. We need everything in terms of x. So we need the radius in terms of x and the height in terms of x in order to get our rate of change in terms of x. What is the radius in terms of x then? So what is, afraid that won't show up if I do it, so I'll do it in white, big, thick white. What is the radius of the shell? I usually don't write in white. Kind of soft and fun. All right, so how do we rewrite r in terms of x? It is the current value of x. Is that what you're seeing? It's the current value of x. What about the height? So what is the height of our current shell? So it's right here. Yeah, so it's right. Remember that we said the height of the shell is the value of the function at the inner radius of the shell. So it's just going to be whatever f of x is. So that's our rate of change function. 2 pi x f of x is our rate of change function. So if this f of x is, say, x squared, let's make it x cubed. Something different. All right, so if that rate of change is x cubed, goes to 0, 0, and then it's going out here to this point is 1, 1. Then now we've got our rate of change function is 2 pi x times x cubed. 2 pi x to the 4th. We've got our rate of change function for this volume as x increases from 0 to 1. So that's our rate of change function. What about our volume function? So v of x equals then, use what we had before. If we've got the rate of change of volume, how can we write the volume function? Yes, sir? Integral from? Do we want 0 to 1? 0, so we want the function. We want to know the volume for any value of x. What's that? Okay, so it will be 0. Yeah, you're right. We could start at any value a. You're right. So let's go ahead and start at 0. Right there. Okay. And so then it'll be the integral from 0 to x of r sub v x dx. Won't work, right? Won't work. Need a new dummy variable for values of x that are going to vary from 0 up to x. Right? If we put x in there, we're just going to get a constant rate equal to the rate at the current value of x. We don't want that. So then we can write down, we got 0 to x, 2 pi t to the 4th dt. Now, say I want the volume of the finished product, right? I want the volume of the finished product. This over here. So imagine that thing filled in now. It's filled in with our cylinders. They're all wrapped around each other, right? Each one wraps around the ones before it. And now I want the volume of the finished product. How could I represent that with function notation? What's the value of the total volume all the way out to 1? How could I use function notation to represent that? He's offered up v of 1. Is v of 1 what I'm talking about? Yep, v of 1. And how can I, in the rule then, that would be the integral from 0 to 1, 2 pi t to the 4th dt. And that's a number, right? It's the accumulation when the current value of x is 1, right? It's the accumulation of volume when the current value of x is 1. All right, so then we can have GC find out what that is for us, okay? So as far as we know right now, we're just going to stick with this. What's this called? Open form. This is an open form expression, which doesn't lend itself to computing function values easily. It's more reflective of the process, right? The process of accumulating all these bits of volume. And so it doesn't really lend itself to plug in 1, get a value. Plug in 5, get a value. All right? But GC can do that for us. So in GC, let me show you how you do that. So I'll just open up a new window here. So we can say our volume use control 9 to define functions, equals, all right. For integral, you control shift I. We're going to from 0 to x, what do we say? 2 pi t to the 4th, is that right? And we want dt. Is that what we came up with? Is that accurate? Okay, so we've defined that function, and now all we have to do, if we want the finished product, if we want the volume of the finished product when the current value of x is 1, we can just put in v of 1. There it is, 1.25664. That's the volume of that filled empty shell. What about halfway? So I can do v of 0.5. So when the current value of x is 0.5, the accumulated volume up to, so this is like just taking that thing for a radius of 0.5 and just looking at that much volume, 0.03927. Any questions? Okay, let's look at, going on with that example, what about if we took delta y? Now, so instead of looking at delta x intervals, what if we looked at delta y intervals? So let's go back to, I'll just use this. So we'll just, so now we're gonna look, I'm just gonna draw one. Suppose the current value of y is here, okay? So here's the current value of y. Now we're gonna think of y increasing through delta y intervals, okay? Now y is gonna be increasing through delta y intervals. And so what is the, so let's say here's a delta y interval. Okay, and we're going to take what? Well, we got to draw this whole thing, right? So we imagine the whole thing rotated. Like this. Okay, and so we have a, here we are at the current, this is the start of that current interval, and here's how much we've gone through it. And so, uh-oh, but I'm going to be over here, right? That's not, the empty shell is over here, so I don't want that. I want this over here. So here's current value of y, here's the value of y at the start, so I'm going to draw this. So that's the rectangle or the slice for the current value. I meant to do it to y. Yeah, so this is the current value of y is the top of that thing. The bottom is the start of that delta y interval. And so as the region rotates around the y-axis, that thing will rotate as well and form a cylinder, right? A right cylinder. And so can we sketch that? So over here at 180 degrees or at pi radians, it's going to be like that. And so can we sketch the whole thing? Can we sketch the whole thing? Can you imagine what it will look like? What that element, that cylinder will look like? I'll do it in red, so we're, I don't know if red shows up. Does it show up as red? Okay. So like that. And then like this. Okay, and then the inside here, there's going to be what, like a giant hole in it. Do you see that? So let me draw a better version over here. It's going to look like this. something like that. That's what we're imagining, okay? And so we have to imagine now because you're not going to have an animation for every problem that you do. So as y increases, and this is in the current interval, and that the volume of that cylinder increases, as y increases, what dimension of this cylinder will increase? R or height or both? Just height, right? Because that radius, that inner and outer radius are going to be fixed in the current interval. And so as y increases, the height of that thing is going to increase. And then the next one might have the next delta y interval may have different radii, but they'll stay fixed in the next interval, and the height will increase through that one. So as y increases, it's going to be the heights of each current cylinder that's going to increase. Okay? So if the height is increased, so let's write that, as y increases, only h increases. And what is h here? What is the height of these things? What's increasing through the current delta y interval? What is h? What do we call that? In the current interval. Delta y interval. We're increasing through there. What is that? Yeah? Nope, because it's going to the height is going to start from here. It's not going to start from x equals 0. No, that's not the difference between two functions, right? So we got the current location of this from the y value here, but then that's all we get, and then we start increasing that, the height of that, and what's that going to be? dy, right? dy. The height is going to be dy. dy is going to increase through delta y intervals. When you get to the next delta y interval, dy is back to 0. And then dy increases from 0 to delta y. And then you start the next interval, and dy increases from 0 to delta y. Right? Okay, so as that happens then, what's the rate of change of volume of this element? What's the rate of change of volume of this element? Remember? So if only the height is increasing as y increases, what's the rate of change? Area of the base, like you can do the area of this, the top of this thing. Okay, so what is that? That's going to be, well, that's area of one circle minus the area of another, right? So we're going to have pi r outer squared minus pi r inner squared. And that's going to be our rate of change. Okay, what is the outer radius here? 1. Stays 1 for every single cylinder. Do you see that? The outer radius stays the same for all the cylinders. Okay, inner radius is what? So what is that inner radius from, say, here, blue, here to here? What is that from there to there? So when you start at the y-axis and head out to the point on the function, what is that? That's a really simple thing. What is that? The x-coordinate. That's just the x-coordinate of that point, right? X is how far right or left you go from the y-axis. So that inner radius of that thing is just the x-coordinate on our curve. But, so we can write that. Let's write that. Pi x squared. And so now our first term is just pi. But we need this rate function in terms of y. So we need x squared in terms of y for this thing right here. Or x, so let's just focus on x. So we're going to square it because it's the radius squared. But what is x in terms of y? This was the function x squared. So now we need x in terms of y. What is that? radical y. If y equals x squared, then x equals the square root of y. Plus or minus, but we're in the first quadrant, so we'll just take the plus, right? And it's a dimension, right? It's a distance, so it's just the plus radical. So we can substitute in radical y for x, and now we've got a rate function in terms of y. And with our rate function, we can easily write the volume. So volume as a function of y equals. In the end, yeah, so yeah, you could simplify that to pi y, right? But I just wanted to show you that. So the square comes from the fact that we're squaring the radius in the area of a circle. And so then I just wanted to show you that, yeah, the radius is x, which is square root of y, and then we're going to square it, so we're going to be back to y, right? Because that's what x squared equals. X squared equals y. That's right. Okay, so then the volume formula will be, everyone write it down. See if you can write down. What's going to be the volume function for building this thing in terms of y, right? For building cylinders through delta y intervals. What's going to be the volume in this case? List of names. So let's see here. How about this young lady in the blue shirt right here with the green pencil? Yes, that's you. Did you get it? Did you get a start? Just anything? You tell me anything about it? Integral from 0 to y. And then what are we going to have there? So every time we set up an integral, every time we set up a net accumulation function, what's the key ingredient? Rate of change of the accumulation, which we just found, right? The key ingredient to every net accumulation function is the rate of change of net accumulation, right? Am I done? Oh yeah, thank you. Right, so I blew it, right? I can't use that variable. Blew it, so let's use u this time. If you use t, that's fine. I'll just use u for something else. Doesn't matter. Some other free variable that's gonna, what is it gonna represent? It's gonna represent values of y that change from 0 to y, right? Okay, and so then if I want to get the final product, again, if I want to find out, this is the 0.11, I want to know what the volume of the solid is when the current value of y is 1, kind of when we get done, right? How do I represent that? We have 1. And what does it equal? We already know. We already know. Want me to prove it to you? So if we put this function in and do v of 1 for this, different integral, right? Different integral, but it's calculating the same volume. We just filled it a different way. We should get the same thing. We should get the same answer. So now, let's call this w. W of y equals Control-Shift-I from 0 to y of pi minus, can I just say pi u, right? Because square root of u squared. So is that accurate? Okay, so what about w of 1? We think that's going to be the same. It ought to be as before. And it's not. What did we do wrong? Something wrong. Oh, because it's not cubed. It's not squared. It was the cube, right? I changed the function. Function was x cubed. So we want to keep that same function, x cubed. And so what is x? X is the cube root of y. So then our rate function becomes the cube root of y squared. The cube root of y squared. And then we'll have the cube root of u squared. And so if I come in here and put that, what is that? U to the 2/3. That should get it for us. Look at that. Now it's the same, right? So got to have the same function to get the same result. All right. What about w of a half? So v of a half. So let's look at that thing again. Not that thing. Where'd it go? Oh, I was working on it. Let's see. Where's the one I was doing? This one. So imagine the filled shell. V of a half was this 0.03. What about W of 1/2? You imagine that's going to be greater or less than V of 1/2? Sorry, that's so dark. It's lighter on my screen. Why? Yeah, what kind of at the beginning those elements when we did delta x intervals, those elements at the beginning, because this thing was so low, right? Small volumes, right? Because the heights of each one were small. But again, the radius is increasing through each interval. So, but if we do w of a half, what are we doing? We're starting with the bottom, right? And so w of a half is going to be all this volume below this. It should be a lot bigger than 0.036. Does that make sense? Yeah. More than half of the total volume is achieved when y is halfway up, right? When the current value of y is halfway up, we got way more than half of all the volume. But starting from x values coming out, most of the volume, right, is on the outside, out at x equals 1. So we got very little volume, 0.039, when we do x equals a half. But when we get to 1, we get the same amount because it's the same filled shell. Okay, let's look at one more example here. Let's look at sine x. So here's sine x from 0 to pi. And I want to rotate this one about the x-axis. I want to rotate this about the x-axis. So we rotate this about the x-axis. Here's what it's going to look like. Ready? Watch. And we're just thinking about creating the empty shell. So we're gonna, that thing is kind of falling towards you. It's pinned at the ends. So let me give it a turn here so you can see. So see the empty shell? It's so dark. All right. Waka waka. Am I dating myself? All right, so notice we rotate around the x-axis, and it makes like what? Like a cough drop or some kind of seed pod or something like that. Imagine it as an empty shell, okay? As an empty shell. And now I want to use delta x intervals. Delta x intervals. I want to create cylinders through delta x intervals to fill this thing, right? To fill it. Got the empty cylinder. Now I'm going to fill it. So let's look at. Here we go. So imagine that thing that we had, and here we go. Here's how we're going to fill it. Okay, and then in the current, so we've got the previously accumulated volumes of cylinders, and then we have the current interval, right? In the current interval, how is that cylinder changing? Is its radius changing? Is its height changing, or both? Is its radius changing? Is its height changing, or both? You should be thinking just the height. Just the height is changing. Okay, watch it again. So in every current interval, as x increases, the radius stays constant, and as x increases, the height of that thing. Now it's turned on its side, so the height is to the side, but the height of that thing is increasing as x increases. All right? So this is sine x. We want to write the rate of change, right? The rate of change of volume with respect to x. Why? Because we got delta x intervals. So think of that cylinder in the current interval. That's kind of blue. Do you see it's blue and all the other ones are pink? All right, it's blue. So the rate of change in the current interval is going to be what? What's the rate of change of that one cylinder as x increases? Area of the base. It's just tipped up on its side now, but it's still the area of the base. And what's the area of the base of this thing? What is it? It's going to be pi r squared, right? Pi. So now we just need r. What is r? What's the radius of our disk? The y value, right? It's from the x-axis up to the curve. This is going to be the y value, which is the function of x. So you could write y here, f of x. And then to get that function as a function of x, we're going to write pi times sine x squared. And now, so this is pi, x equals pi. So I want you to write the volume function in terms of x. And then I want you to use function notation to represent the volume of the whole seed pod, volume of the whole seed pod. Question? What do you guys think? So, okay. So how would you describe the radius of a circle? What is the radius of a circle? From where to where? So are you seeing that this is the radius? Is that the radius of the circle? But it sounds like you're arguing that the radius should be from here to here, so that it'll be 2 sine x. So are you seeing that the radius is from here to here? That's not the radius, right? That's a diameter, right? So you're confusing diameter and radius. The radius is truly from the middle, which will be the x-axis, up to the top. So it's just
really common mistake. So it's kind of good that you pointed that we had that conversation. People do that all the time. Oh yeah, I have to integrate from the bottom to the top. No, if you're doing radius, you have to integrate from where the radius was nothing, from the smallest radius to the biggest radius.
okay. So how about here in the maroon shirt? Did you get it? Tell me. This is what I heard her say. Is that right? Got it? And so how can we represent the volume of the whole lemon drop, or the whole seed pod? V of pi. V of pi then would give us the finished product. But the great thing about this function is we can get the volume for any current value of x from 0 up, if we want half of it, we'll take from 0 to pi over 2. In this case, because there's symmetry, it will give us half the volume. Right? If we just want up to x equals, a half, we do v of a half, and it'll give us just that much of it. Something like this. Maybe that's about 1, so somewhere around here is x equals a half. If we want just that much volume up to x equals 1/2, then v of 1/2 will represent that, and then GC can find it for us. Question?
So I think it was on number 4 on our homework.
Okay.
There's a question about what is the independent variable in one of these scenarios. So which one is the
Independent variable is always the variable that we're going to choose to increase through. So we did delta x intervals, and x is increasing through delta x intervals. That's our independent variable. So in the last example I did was y, because we did y. Okay, any other questions about these examples? Okay, let's look at your sheet. Example, I want to point something out. If we were to do delta y intervals on this one, let's just quickly talk about that. So what will happen there? So again, I'm still going to rotate around the x-axis, but now I'm going to do delta y intervals. And so here I'm drawing one shell. Like that. So we got one of those shells. I'm drawing one of those shells there. Okay? As y increases, what increases of this shell? The height or the radius or both? Radius only, right? Height is fixed in the current delta y interval. As y increases, our radius is growing. Therefore, rate of change of volume is, in terms of y, 2 pi RH. Okay, what is the radius? It's the y value, right? The radius is from the x-axis to the inner radius of our shell, which is 2 pi y. And what's the height? So the height is from here to here. So do you see that height is now a change in x? It's a large change in x. So how do we calculate a change in x? How would you? A big change in x would be x final minus x initial. So this would be x final here, and this would be x initial. But we need to get those in terms of y. So we've got our function, y equals sine x. And I need to get x in terms of y. Arc sine. But notice that both of these, the x initial is the x value on the sine curve, and the x final is the x value on the sine curve. So arc sine is only defined from negative pi over 2 to pi over 2. So the arc sine will give me this one. Then I got to do a song and dance to figure out what this one is. But we can do it by symmetry. But do you see that this is getting kind of ugly fast, right? This is getting, we can do it, right? This initial x will be arc sine. This final will actually be by symmetry. It'll be pi minus arc sine by symmetry of that. Yes, so that's why I said it's going to be pi minus arc sine. So yeah, so whatever distance this is arc sine from here to here. Well, that's the same distance there. So if you take pi minus that, you get. See that? Anyway, so that I don't want to. We can talk about it later if you're. But anyway, so the point is that this choice for filling this empty shell the far better choice is delta x intervals. It was much easier. Here we've got the situation where it's very inconvenient to use delta y intervals because you have to mess with arcsine and it gets more complicated. It can be done, you know, it can be done. It would be 2 pi y times arcsine of y minus pi minus arcsine of y. But who wants to do all that? Okay? And it makes for a more complicated function. Okay? Makes for a more complicated integral function. Okay, so the point is that these can be set up in two different ways, delta x intervals and delta y intervals, but sometimes one is much more convenient than the other. And so you want to kind of be forward thinking, right? So you got to think about it. And if you get into this case where it's a situation where, oh, I got two x values to get, they're both from the same function. Maybe that's an indication, hey, use the other variable as your independent variable. Okay, does that make sense? So now our 20-minute activity here, we're down to 3 minutes. So let's just get a little bit started on example part 1. So maybe for time's sake, I'll draw the sketch. So we got y equals x squared, that's g of x. That goes through 1, 1. So g of x goes through 1, 1, and 2, 4. So it looks something like this. And then x plus 2 has a y-intercept of 2, and it's actually going to come up and also go through the point 2, 4. Now we're going to rotate that about the y-axis. When we rotate that about the y-axis, what will our shell look like? So you'll get your empty shell will look something like this. And where's the empty shell? Is it in this top part here, or is it down in this bottom part here? The place we're going to fill up. Are we going to fill up this cone up on top, or are we going to fill up this kind of jug down here? Yeah, this is our empty shell down here. That's what you get for this region rotated. So let's just, obviously we can't finish it, but let's just talk about choice here. Choice, delta x intervals or delta y intervals? Delta x or delta y? So let me show you the animation and then we can decide, okay? So we're going to should we use delta x or delta y? What are the implications of using each? What are the implications of using each? So let's do delta x first. Here's what delta x looks like. As x increases, what's changing about these cylinders? Is the height changing? No. For the current value of x, the radius changes. The radius increases. Okay? And so what would the height of each cylinder be? How would you get the height of one cylinder? Or the other way around. F of x minus g of x would be your height. Your radius would simply be distance from y to the curve, y-axis, is x, right? Your radius will be x. Your height will be f of x minus g of x. Smooth sailing or problems? Smooth sailing, okay? What about if we do delta y intervals? What happens here? So first of all, each Oh, those are really big. Whoa. Each cylinder, does its radius increase or its height increase? As y increases, the height of the cylinder increases, okay? And the radius stays the same. What about this one? What's different about this? So here, what about, so these cylinders have a hole, right? What about these cylinders? They're just discs without a hole. So in order to use delta y intervals, what we're going to have to accumulate volume through these intervals where there's no hole, or the y-axis is our boundary. But then when we get to the function f of x as the inner radius, we're going to have to write a new rate function, right? You're going to have two rate functions. You have the rate function for y values below the y-intercept of f. And then when you get to the y-intercept of f, you're going to have a new rate function as y increases. Meaning that our accumulation function of volume will have to be volume in terms of y. What will the structure of that be? If we got two different rate functions over two different y intervals. Yeah, so it's going to be a piecewise function, right? It's going to be a piecewise function. You're going to have to accumulate according to the first rate, and then in the second, you're going to have a new rate of change, and so you're going to have all the accumulation from the first plus the new net accumulation in the second part. What do you want to do, delta x or delta y? Delta x, smooth sailing. But we should be able to do this. We should be able to do this also. But if you had to make the choice, choose delta x. Have a great weekend.